Hi there, you okay? Okay, let's start with our fourth lesson about the special theory of relativity. Well, we have seen that the relative motion introduces some incredible new issues in mechanics. In particular, we have seen that the assumption about the constants of the speed of light implies that the time and the space measured by different observers are not the same. And we have found the transformation formula from the proper time to the rest time of an observer, that is the Lorentz factor, the so-called Lorentz factor, that is equal to the square root of 1 minus v squared over c squared. But we will find it again and again in what's following. Today we want to introduce another method to evaluate the relativistic effects using the so-called Minkowski approach to the space-time. Minkowski was a German, probably, sorry, not German, but he was from Austria, and he died quite young after a serious disease during the First World War. But fortunately, he had time to leave to us an important vision of the space-time. If you consider it just a point moving along a straight line, remember that we are dealing with the special theory of relativity, so we consider just only linear motion with constant speed. But if we consider a point P moving with a certain speed v along a straight line, okay, we know that the movement of the point along the line is described by a position, by its position on this straight line. And the position varies with time, okay? So if we want to represent this fact in a two-dimensional graph, what we do? We simply do this. We could call, okay, the position of the point on this line, we call it x, and x will correspond to this horizontal line, and we can label t the instant of time corresponding to the different points along the line. Just to see, in the case of the movement of the point P, we can imagine that at t equals 0, the position of the point is x equals 0. So we consider the point P starting at the origin of the axis, like this. So this is the origin, and correspond to the initial position of the point P. Okay. If after a certain time, a certain interval of time, let's call it t1, the position of the point is at a certain position, is at a certain point x1 on the horizontal axis, okay, we can join these two coordinates and we state that the point P at the time t1 is in the point x1. Remember that we are considering just only a one-dimensional motion along the straight line, and the fact that we have this picture in two dimensions is only just because we are considering the time the other dimension. This is the reason why this is called a space-time representation, because we have space, just one dimension, and time. Okay, if we consider a motion in two dimensions, suppose that we add another coordinate y here, and these are two special coordinates, and the point can move on this plane here. Adding the time, okay, we obtain a surface indicating the position, a curve in the space-time, where in this case we have two special dimensions and one time dimension. If we add the third special coordinate z, it's impossible to represent because we have already three special dimensions, and we cannot add a fourth one, at least in the usual way of represent ordinary pictures, because we are three-dimensional beings, and we cannot draw the fourth one. Okay, so but for a moment let's stay in the simple situation where we have just only one direction, one special direction, plus time. Okay, so you can see that if the point is moving with a constant speed, it will run for equal intervals of space in equal intervals of time. Okay, so what happened is that the result is the point moving, the position P1, P2, the point moving along a straight line in the space-time diagram. Okay? Well, but there is a better way to represent this situation. As you know, from the elementary basic physics, classical physics, the velocity, the speed of a point, is the ratio between the position and the time. Okay? So in this case, in particular, we see that the ratio between, for instance, x1 and t1, or x2 over t2, will be always the same, because we see that x1 divided by t1 is equal to x2 divided by t2, and so on. And this is the definition of speed of the body, of the point. Well, but to have, as I was saying, a better representation, we can consider, instead of the time t expressed, for instance, in seconds, and the space x in meters, so we should have the velocity expressed in meters per second. We can we can label the time coordinate with the product of the speed of light c times the ordinary time t. In this way, instead of having this ratio, we have another kind of ratio. We have the ratio between x and c over t. But as we know that x over t is v, this ratio here is v over c. That is quite better than v alone, because in this way here we know that the ratio of these two coordinates, this time you have ct1 and you have ct2 eventually here, and the ratio between this and this in this case will be exactly 1 if the speed is equal c, if the speed of the point is equal c. So what does it mean exactly? It means that if the point moving along the straight line is a photon, is a beam of light, the ratio between this and this will be 1, because c over c is equal to 1. And if this is 1, the ratio between the vertical, the horizontal side and the vertical side is equal to 1, we know that this is 45 degrees angle. Okay? This means that if I use this Minkowski diagram to represent the motion of a body in the space-time, I will have that the light moves always along 45 degrees inclined straight line. Okay, so this is the moment, the point corresponding to the position x equals 0 here at time t equals 0 now, and these are all the points that a beam of light cover during its trip. Okay, what about an ordinary body? A massive body. So we know that all the physical objects that have a mass cannot go faster than light. So it is impossible for them to do like this. Because in this case, as you easily see, the ratio between the x and the product ct, the ratio between this and this, it is greater than 1, because this is bigger than this. So the angle of the line corresponding to the motion of a massive body starting from here cannot have an inclination, an angle less than 45 degrees. So this portion here is forbidden, because nothing can go faster than light. This is the limit, this is the light. All the other objects, for instance, a body of mass m, can move like this. This is the motion of a point having a certain mass. Okay? At the limit, it can go very near to the speed of light, but never reach it. Okay? So this is the good part of the diagram. This is forbidden. Well, we can complete this representation considering that instead of having something moving from left toward right, we can have the opposite direction movement. In this case, it's quite trivial to see that the light can go in the other direction with a 45 degrees angle, but nothing can go faster than light, so all this portion here is forbidden. Okay? Good. What about the past? Why I say the past? Because this point here corresponds to t equals 0. So it is now. This is the future. This is t equal 1, 2, 3, 4, 5, infinity. This is t minus 1, minus 2, minus the negative numbers represent obviously the past of this point here. Well, it is the same in the past because a light beam coming from the past cannot go faster than c, and this is the straight line. So nothing can go like this, that is excluded. The same on the other side, on the other direction. So the final result is that the space-time connected to this point here, that is x equals 0, t equals 0, that corresponds to say here, now, all the physical space-time allowed for this point here is this one, this region and this region. This is the past of x equals 0, t equals 0, and this is the future of the same x equals 0, t equals 0. Okay? From now on, we will call the point in the space-time with the name event. Normally a point is a point in the ordinary space. An event is a point in the space-time. It is quite reasonable to use the name event because the event here now is just me here in Cambridge talking now about special relativity. Okay? Another event could be, for instance, a point here that is the I don't know. So I don't know. Let's say the discovery of America. The discovery of America is in my past. Okay. Another event could be, for instance, a person in New York that is eating an apple right now. This is in the forbidden zone, because suppose that New York is here, okay, and if the person that is eating the apple right now in New York, it is far from me in space, but is exactly in the same instant of t. Now, and it is disconnected from me. It is in the forbidden zone because nothing can reach this event instantaneously, because light to reach him needs a certain amount of time, and to find which time I have to do like this. Go here and I divide the result of this by c and I get the t, the time to reach it. So this is quite interesting to consider. The person in New York is not physically disconnected by me, in the sense that I can reach him with a telephone call. But when he answers the telephone, it is not the same event. It is the event here, because the telephone call is going at the speed of light, probably something less, so it is just anyway more or less here. So it is clear the events are not persons, animals, objects, are points in the space-time. Okay? A future event in my permitted zone, it is, for instance, very simply me standing at rest, standing still here while I am talking in this short lesson. And for instance, I see that if I stay still in the point where I am now, the time passes, and so I can reach this point here. That is the event. Stefano is talking again and again, is talking about special relativity, but it is not more the event when he was talking about the Minkowski, the introduction of Minkowski space, but it's just quite at the end of the lecture. Okay, and this is my future. Another future of mine is if I leave this place now, I go to the toilet, and the toilet is quite near, it is here, and I go slowly to the toilet compared to the speed of light, so I go like this. And this is the event in my future, Stefano, in the toilet, 2 minutes after the t equals 0, x equals 0 event. Okay, I guess it's quite clear, even if the blackboard now is just a bit confused, but anyway, this allowed, this permitted zone is called the light cone. Why is a cone? Because just if you add another dimension, special dimension, as I said before, you get a plane, and so you can represent like a cone. But doesn't matter, even if you consider just only one special dimension and time, you have a sort of cone that is like this. Okay? Remember that in geometry, a cone is something like this. We are used to think about a cone like a picture like this. This is a finite portion of cone, but the geometrical entity cone is something like that. The continuous after the vertex like this, and no limit like this. Is continuous to infinity in both the directions. Okay, so this is exactly the light cone. Okay, I think that is better to stop here now, and next time we will see some implication, very interesting implication that we can see using the Minkowski space-time diagrams. Thank you. See you soon.